Hi, everybody. Welcome back. As you can see, I've got the questions from what we looked at in yesterday's class back up here, just in case you have any more questions about them. Please make sure to email me or to ask me any questions you have about them, because that's the key to surviving Orgoland. I mean, having fun in Orgoland on your tour through this beautiful place is that you ask me lots of questions. And they may not have specific office hours, but that's because I'm counting on you reaching out to me whenever you want to meet. Okay? So let's dive into something outside of acid-base world. Let's go back into Orgoland, and now for something completely different. Oh, okay. So this is called nomenclature. This is how to name organic compounds. And again, it's very systematic in its approach, but it's a little confusing at times. And so we will just spend this one lecture on this material, and please feel free to revisit this anytime you want to learn how to name and speak Orgo. So the reason that it's somewhat complexing and a little annoying to me is that here are two chemical names, two completely different names for supposedly completely different compounds. Yet in all reality, I would accept either of these names because they represent the exact same molecule. So nomenclature can be a little tricky. Granted, this one on the right, this one here, is the better way to name this compound. But again, we're just trying to talk to each other in Orgoland. And if I were to give you a name, I'd want you to be able to draw me this structure. And if you gave me the structure, I'd want to be able to write the name. And we can talk to each other this way in Orgoland. This is now our official Orgoland language. Okay? So the official language comes from a very nice place in Switzerland known as IUPAC, and they have a nice office there and building there, and they've actually standardized or tried to standardize the way to name molecules. And so IUPAC has come up with this naming system that involves a root, a suffix, and a number or group or prefix out in front for any pieces of the molecule that are not the root and not part of the suffix. So let's take a look at each one of these parts. And for example, could you draw the structure for 2-methylpentane for me in this box? What line structure would you draw for it using this name? Did you come up with this one? Granted, it doesn't really matter where this CH3 goes, but my numbering was 1, 2, 3, 4, 5. And on carbon 2, there is a CH3 for a methyl. So 2-methylpentane. Let's dive in and figure out how to systematically go from this structure to this name, and from this name to this structure. That's what today is all about. In doing any kind of nomenclature, it's really important, if we're going to try to figure out who's the suffix and who's the prefix, that we have some sense of priority. Which functional group dominates? What if I have multiple functional groups on my molecule? Who's going to be the suffix? Who's going to be the prefix? Who wins? So in this situation, I have a table here that's listed by most dominant suffix. You can see is a carboxylic acid. I love how this means it will never ever be a prefix out in front. It'll always have to be the end of your molecule's name. And so if you ever have a carboxylic acid, it will always it'll always end in oic acid of some kind. But it's not always that case. What if I have an alcohol, for example, that's sitting on my carboxylic acid? If I have an alcohol on my carboxylic acid, it would have to use this prefix for my alcohol, which is hydroxy. But if I have an alcohol that's on an alkane, then the alcohol has higher priority than the alkane, and it would be the suffix, and I would name that molecule with OL at the end of the name and put the alkane somewhere else, like methanol or ethanol. So this is a very important chart. I highly recommend you use it. One of the things I've done with my post-it notes above me is now you might be able to notice I've put my functional groups and the correct order of who has the most dominance, who is the higher suffix priority. Okay, and feel free to add more post-it notes to your wall with their suffix name or their prefix name. Okay, because these are things that we're going to have to get to know, and some of them I'm hoping we will see just by using them a lot. Okay, so it's not something that I would recommend that you actually create a flashcard and you go and try to memorize them all. Hopefully we're just going to use them. So starting systematically, we should find our root of our molecule as well as the suffix, and then we'll be able to deal with the prefix. Okay, so to find the root of your alkane, or any molecule in general in Orgoland, you want to find the longest continuous carbon chain in the compound, and therefore give it one of these beautiful root names, as we've seen, like methanol or methane, ethane, propane. This is as many as you need to know. So again, great for the post-it notes. Put them up there somewhere and get all of these number of carbons in your head, and you will begin to speak Orgo very quickly. If there are two more chains of equal length, choose the chain that produces the most branches off the chain. We will see this in an example coming up soon. But there will also always be possibilities, just like I showed you on the first slide, where the naming can be slightly different for the same structure. This is a key point here. Try to create more branches, then we'll be talking the same language. So here is this summarized here. Find the longest continuous carbon chain. If there are two more chains of equal length, so going around the length, you find them the same, choose the one that has the most different pieces falling off of it, and number the carbons in the root starting from the end that produces the lowest numbers that we would assign to all the other groups around it with prefixes. So your molecule, and the reason you can go back to that second slide I showed you, the reason I like the molecule on the right is it gave the root a low number. It gave the suffix a low number. So giving low numbers to these roots and suffix is really, really important. Okay, so let's play with this molecule. How would you number this molecule? Can you spy the root? What's the longest continuous chain? Ready? Here it comes. Did you spy that it does not have to go straight across? It is not the 4 carbons straight in a row, but it's starting at the top and going down. And I get 5 carbons in that continuous chain. Okay, so pent is a 5 carbon chain. This is nothing but an alkane chain, no other functional group. So it is going to end with the suffix ane, pentane. And hanging off carbon 3 in either direction you go is going to be a methyl on this one. Okay, how about this one? Can you tell me the longest continuous carbon chain here? Cool. I bet you found it. Now that you're not looking straight across, you're looking for all sorts of ups and downs, lefts and rights. So here is one of the longest chains. I could go 8 carbons in a row here with one group branching off of it. That's an 8 carbon chain. Maybe you saw that one, or maybe you spied this one, which has 8 carbons in a row in this continuous chain. But notice this one has 2 branches hanging off of it, the CH3, and what group is that? Yes, that's a propyl group, 3 carbon propyl. And so really we don't like the one on the left, we really like the one on the right, okay, because it has the most branches, and that's going to help us define these two. And we'll start talking about how to number these groups hanging off, these branches hanging off the root. And again, all of these are alkanes, so all of these would end in a suffix ane. So all you have to do is know how many, what's the name for 8 carbons in a row? ane. So these are octanes. Which structure has the longest carbon chain or root in these two examples? Okay. Did you try it? Count them all up. See if you came up with what I found. I found that both of these have 7 carbon chains, just in completely different directions. So neither, they're identical roots. Granted, they might be slightly different names, but then if you look closely as to who is attached as a group, I thought I'd show you that they both the same name. These are actually identical structures because they have the same root. They are 7 carbon chains, heptanes, and the actual lowest number I can give to all the groups coming off are 3, 5, and 4, and so it's exactly the same compound, just spun around, as we talked about with our alkanes. These single bonds like to spin, so they can spin and be in a different orientation. Having fun yet? Nomenclature! Yes! Okay, so let's now start combining suffix and root and looking at a little more complicated things than just alkanes. Keep in mind the suffix group must be attached to the root, not some other branch or group. It has to be part of that longest chain. And therefore you want to incorporate it into the longest chain, even if it's not the longest chain. It has to be part of the longest chain, the root. Your suffix has to be attached to your root. Okay? So we've already seen alkanes. We already talked about OL for alcohols, oic acid for carboxylic acids. So these are just a few. And what we want to do is once you put the suffix or that functional group on your root, you want to try to give it the lowest number possible in your counting on the chain. Okay? So this molecule here is, again, just a boring alkane. But here now I have a hexane, and I could number it from one side to the other. And I actually want to number this one going 1, 2, 3 to get to my CH3 here. And not 1, 2, 3, 4. How about this one down here? This is an alcohol. What did you guys come up with? This is butane 1-ol or 1-butanol. The one can go way out in front because there is only one other species functional group that's different than the butane chain, and that's the suffix, the OL. So the one way out in front represents that you want to put the alcohol on carbon 1, which is great. You do not want to put it on carbon 4 going the other way. Bad news. Okay, how about this one? Try this one. Cool, you done? Yeah, have you given it a shot? Tried this nomenclature, and again, like Orgoland language, you just got to keep practicing it. Did you come up with this one? 3-methylbutanoic acid. And most importantly, I wanted you to make sure that you counted this carbon 1, 2, 3, and it doesn't even matter if you go up to 4, but that carboxylic acid carbon has to be carbon 1 in every single structure that you ever draw with a carboxylic acid. Has to be carbon 1. Okay? And then we can name that blue 3-methyl, and we don't care about the group as much. It's lower in priority. It's a systematic rule that we're following. It has rules. Some of you will like these rules because they're very dependable and never change. So we will not do 2-methyl-4-butanoic acid. That is out. All right, you ready? We've talked about root, we've talked about suffix, and again, there's tons of different suffixes. So try not to get too overwhelmed with it. You have that chart at the handy. And the best news is on every midterm that you have, you get 1 page of 8.5 by 11 notes. Because I don't want you to have to memorize that table. Take that table of suffix and prefix in order and put it on your 1 page of notes for your exam. There's some things that are just not worth memorizing. Okay? Joy, a page of notes for your exam. Okay, cool. What about groups? Groups are coming off as branches off of your root. And it's important now to recognize that if they're a group, they're very low in priority. They're not the suffix. And so alkanes will always end in a YL. So that's how we end the name of an alkane when it gets in part of the group. And again, we have to memorize or not and put this on our 1 page of notes for the final exam. Very cool. This little chart of meth, eth, prop, bute, pent, hex, and so that you can spy that this would be a methyl. And if I gave you a 2-carbon group hanging off your root, you would see this as an ethyl, and so on, pentyl. Okay, and so this is how we will name them. Add the YL. So if you have more than one alkene or alkane group hanging off your root, you want to list them alphabetically. And this is something that IUPAC is really, really stingy about, like ethyl E before methyl M. If you have these 2 groups, you would write the ethyl piece, then the methyl, then the root and the suffix. I'm less tenuous, less strict about this because I feel even if you didn't do it alphabetical, I'd be able to draw the structure. But try. These are the rules that IUPAC has laid down. Try. If you have multiple identical groups, such as 2 methyls, even if they're on different carbons in your root somewhere, you have 2 methyl groups hanging off as groups, you would want to name them dimethyl. And then you would want to put and name them using the M, not the D, when you're doing your alphabetizing of these groups. Okay? So that's what this is for. Don't use the tri or the di. Use the actual group's original name. The tri and the di are redundancies that are built in because you're also going to have to tell me that where are the 2 methyls? They're on carbon 2 and 4 dimethyl. So 2,4 dimethyl is something you might have to actually draw. What do you think for this one? Take all this knowledge, spit it out onto this little square and see if you can come up with a name for this one. And are you a nomenclature god? Do you have this gene in you? We're going to find out. It's not necessarily in me. It takes a lot of effort for me to do nomenclature. Okay, ready? Here comes the answer to this one. 5-ethyl, 2,5-dimethyl octane. Notice ethyl comes before methyl. There's an octane chain, and this is the lowest number of in the octane order. Okay, and please feel free to bring this to class if you have questions about this one. Let's play with alkenes a little bit. We've just talked about alkanes and a little bit of alcohols and a little bit of carboxylic acids, but alkenes have a very unique nomenclature system, and we will see alkenes a lot in Orgoland this summer. So let's make sure we're clear about these. We still want to find the longest chain and the longest root, but now the importance is, as always, this is going to have this name has to go through the alkene. I must go through, and it must contain both carbons in the numbering process. So here are 2 possible names, 3-butene or 1-butene. And the key is I have to go through the double bond in the numbering, and I want to give it the lowest possible numbers that I can have. So this is why this one started at 3, because it goes 3-butene, knowing that the 4th one is the other double bond carbon. 1. Which one of these is right? Lowest number, higher number. So we're not going to use 3-butene. The correct name for this molecule would be 1-butene. Okay. You could also name it but-1-ene. You can stick the number of where that actual functional group is showing up right next to the name if you'd like. That's fine too. So try this one on the bottom here. See if you can figure out what is the name of this molecule. And notice it's got a group and an alkene and a root and a suffix. Having fun yet? Yes. I kind of like this part. All right. Ready? Go. What did you come up with? I don't mind either of these names. 7-methyl-2-octene, 7-methyl-octuene. Notice I have to go, the 7 has to be the methyl way out there because I want this to be a low number. So 1, 2, 3, go through the double bond, 2 to 3, 2-octene is the actual root and suffix, and then I start naming my groups around it. How are we doing? Little side note. This alkene actually has 2 structural isomers. As you recall, we can't rotate that double bond. Remember my pirate ship back there, the pirate ship, pi bond. Can't rotate pi bond. So there are actually 2 possible names for this molecule and 2 possible structural isomers for this, which we'll see in chapter 6. And when we start diving into the shape of these molecules, as well as their name. All right, let me throw the kitchen sink at you, see how we're doing. What if we had really complex groups hanging off? Branches within branches within branches. Oh my God, okay. So nomenclature could go way into the deep end, and I'm gonna show you just a few more slides on the things that I want you to be able to do for our Orgoland tour. But I wanna be very clear. We are not going to become IUPAC nomenclature gods. I want you to become Orgoland nomenclature gods. So let's go through the complex groups that are possible here, and then we'll talk a little bit about naming other functional groups. So here, very big alkane. Notice there's no other functional group. So this is already going to end in an ANE. And all I want you to do is start with finding the root. What's the longest chain possible? Okay, so this is one possible chain. I think this is the only one that gives you 9 different carbons. I mean, excuse me, 9 carbons in a row. If you tried to go in any other path, it would be a shorter chain. I think, yeah, okay. So there are 9 different ones here, and now we got this green methyl hanging off, and we have this blue branch hanging off that has a methyl hanging off the branch. So how do we name this blue branch in our final name for this molecule? I have to be able to name it so that you can actually draw this structure. That's our goal. So choose the longest chain of the branch. So you can see here, the longest chain here is going to be this propyl group, 1, 2, 3. I can't go up, that would only be 2. So the propyl, and begin numbering the propyl group with the very first carbon being carbon 1 on this branch with a branch. So, and notice I'm paying a lot of attention. It's coming off of this carbon here. So what's the first carbon of that very fancy branch becomes carbon 1. Okay. And then I do the longest root for my branch. And guess what? I have a methyl hanging off my propyl. So we'll still use the YL ending here for this very big complicated group, but it's going to be put in parentheses to encapsulate this as a group, a big branch group that sounds like a group with a root in it already. Already getting fancy. So I want to name this fancy branched group. I highly recommend you do this separately and recognize that there is a methyl hanging off carbon 1 of the propyl. And so this is a 1-methyl propyl. That is the group. And which carbon is it attached to on my root? It is attached to carbon 5. So look what happens to the final name. We have 2-methyl, keeping it nice and low, putting it over there as opposed to counting the other way. And then we put 5 because I want to tell the reader where to put this fancy 1-methyl propyl. So it is 2, 5, 1-methyl propyl nonane. And if you tried to come up with this like just by looking at this structure, I think it's very hard. So I highly recommend you do something systematic where you actually determine the suffix, you determine the root, then you go play with and you write these out separately, 2-methyl, 1-methyl ethyl, and then lastly you put in the 5 for the fancy branch. You do these things systematically, like 1, 2, 3, 4, 5, and then put all the pieces together, because there'll be very fancy, complicated molecules. And I don't expect you to be able to draw it out right at the beginning, but at least figure out all the parts and pieces and then write the final name at the end. I highly recommend that. There's another very popular kind of group that we're going to see in Orgoland, and they're cycloalkanes. There's very popular t-shirts out there that say everything you need to know from organic chemistry is to learn how to draw a cyclohexene ring. That's how popular this ring is. So let's learn how to make sure we name cycloalkanes, because you're going to see a lot. So generally the root, as you heard in my cyclohexane, is the number of carbons in the ring. The prefix is the cyclo, because I can't just say hexane. That would be just a chain. So don't forget the cyclo, often forgotten. And then we look at the branches on the ring to create the smallest sum of the numbers off those branches. So how would you number and name this compound? Give it a shot. Come on, write it out. See what you came up with. It's only practice, practice, practice. Nobody's watching. Okay, did you come up with this name? 1-ethyl 3-methyl cyclopentane. Right? And notice the alphabetized. Again, the numbering of 1 for the ethyl and 3 for the methyl, not really important. I could have done 3 for the ethyl and 1 for the methyl. We're not going to pay attention to this, but what's most important is it went around the ring this way. That's the preferred shortest way to get to that methyl or from the ethyl. But notice if you went the other way, you would have a 1 and a 4. Those numbers are too high. Don't use that one. Okay? So alphabetized, numbered. If I gave you this name, my hope is you'd be able to draw me that structure and vice versa. That's our goal in our Orgoland tour. Okay? Number the branches on the ring to create the smallest sum of all the branch numbers. So this again is just a numbering thing. Try to keep the numbers small. Okay, so this is 2-methylpropyl cycloheptane. Notice I don't even put a 1, because if I have this very bizarre group attached and I only tell you you have a 2-methylpropyl attached to your cycloheptane, you don't need to give me a number where it's attached. It's only one place, and it doesn't matter where on the cycloheptane it's attached. Welcome to, okay, I give you one little, this one's a brain cruncher. If you have a very long chain, then the ring is smaller, the ring becomes a group. Oh, yes. So we're having fun in nomenclature now. So this is a 7-carbon chain with a cyclopentyl group on it. Okay. If I have, like you saw here, a cycloheptane with a propyl chain on it, the cycloheptane became the suffix. If the chain is longer, it becomes the suffix and the dominant root. Okay. Very tricky. One exception to this. If in your ring you have an alkene or you have one of these functional groups, an alcohol, something that is dominant, more dominant than say that heptane chain or pentane chain, then the ring again becomes the dominant root / suffix. So keep an eye for functional groups that pop up into your ring. So even though this is only 5 carbons and you have a 6-carbon chain, there's alkenes in here. And remember, I have to number the alkenes so that I get the lowest number possible And I even name them di because I want to make sure you know there's two, and now you know exactly where they are. So you can see how this gets a little more complicated, but it follows these rules. Let's just keep playing. Now, I wouldn't be a very good Orgoland tour guide if I show you some additional old school terminology that IUPAC doesn't want you to use anymore, but still old school chemists like me have been using this terminology forever, and we're very hard at giving it up. So let me show you what you might see out there in the textbook and also from some old school chemists describing things. This is not too old school. It's still very popular. That when you look at this molecule, we might actually start describing the types of carbons in here. So it's not a nomenclature or a naming thing, but I thought I'd throw it in here as well. That this carbon is only bonded to one carbon, and so it is known as a primary carbon, which can be designated with a 1 and a 0 above it. Okay? And then we have our secondary carbon and our tertiary and our quaternary carbons. So these are another way to describe the types of carbons that are in our molecule. And so in this molecule, I could just say to you, look at the tertiary carbon in this molecule, and there is only one tertiary carbon. And so you'd know exactly which carbon I was referring to. So you're going to see this a lot in Orgoland. The part you might not see a lot, and feel free to take this table and put it on your one page of notes, are the way we abbreviate things like 1-methyl-ethyl, which IUPAC loves for this group over here. Notice it's an ethyl group with a methyl on the first carbon. And they name it isopropyl because they think it looks, when three line structures, it looks like an isosceles triangle. When it branches out, it looks like an isosceles triangle. So they call this isopropyl, and it accounts for all three carbons and hydrogens. That would be an isopropyl group. So you can see, hopefully you can see where they get the name tert-butyl or T-butyl to emphasize the fact that it looks like the shape of a T. So 4 carbons in the shape of a T is a T-butyl group. And then last but not least, we have our beautiful benzene ring down here, which has a systematic group name of a phenyl. And so you will see this name often as the group name associated when benzene is not the suffix of your molecule, but a group. And so phenyl, or pH, is another abbreviation you'll see. You'll see lots of little abbreviations in our world, like methyl sometimes could be abbreviated ME, or ethyl could be abbreviated our ethyl group could be abbreviated, as you can imagine, ET. So welcome to Nomenclature. These are the slang, the nuances, and please ask me any questions as you start drawing these structures, and feel free to use any of these old school terminology in your names if you'd like. All right, time to put it all together. So really, I want to go to our study groups and play with this mostly. But see if you can name these 3 molecules. Okay, I'll give you a second and then we'll see what happens. Okay, so I wanted to show you that the pink is the root, and this is the name that I came up with for this first molecule. Okay, for the others here, I really hope that you had a chance to see these and come to our session and make sure you ask, why are these names the way they are? Did you come up with something slightly different? Could you have used your name? And would I be able to draw the same structure? This is the goal. Okay? Pick the correct name for this compound. Okay? Come to our study groups with your answer. And then let's throw a little more kitchen sink at you. Here's that table again with all the priorities. And really what I'd love for you to do is I'll show you one of these, one or two, but try to see if you can name these now. Just pause the video. Okay, come on back. Let's see if you name the ones on the left over here. This is the name I got for this difunctional group. It has a halide and an alkene, but notice the alkene has a higher priority, and so it will be the suffix. Either of these names are fine. Here, the ketone has a higher priority than the alcohol. So welcome to knowing your functional groups. Being able to spy them is really, really helpful in nomenclature. So if you haven't gotten your post-it notes up on the wall and don't have your functional groups in your head yet, even with this table, life is going to be a little harder for you. Okay, try these other two. I don't think I have them. Nope. Yep. So try these other two on the right. Come to our study group and see if your study group members compare your answers for these two. All right, more practice problems. Can't get enough practice with nomenclature and the language, so these will also pop up in your study group. But I thought I'd give you this one on the right to begin with because it has an ether in it. It's a brand new functional group, and I wanted you to notice that this is called an ethoxy. So it's one more group that we're going to see a little more often than like the halides we'll see, the alkenes we'll see, the alcohols we'll see. So I've tried to lay out the framework for the most popular functional groups you're going to see in Orgoland, but not all of them. So for these two, come to our class, compare with your tour members, and let's see what answers they came up with. Same thing goes for this. Practice, practice, come to class, study groups, see if you try this, come to the class with a final answer already. And if you are a nomenclature god, if you want to know what kind of problem I would put on the exams, see if you can get to here. This is the hardest actual question I would ever ask you, is to name this compound. And if you can name this compound, then you actually are a nomenclature god in Orgoland on our tour group. Give it a shot. Feel free to come to study group and compare answers with one another. Now, as I said, there's much more nomenclature about alkynes, ethers. We talked a little about amines are very popular, other functional groups. I am not going to go through all of them. I have already talked way too long on nomenclature in this one video already. But the PowerPoint slides and the student handout slides that are posted for you will contain a lot more PowerPoint slides looking at each of these functional groups and how to name each of these in case you ever want to reference and come back to them. Go look at the PowerPoint slides from our student handouts and hang on to those. Okay? I hope you enjoyed our introduction into nomenclature. Woo! We're now speaking Orgo. We are about to venture into Orgoland full bore, and I can't wait. It's going to be so exciting. All right. Have a great day. I'll see you later. Bye.